So this is now again from 3.2, and this is part 4, and this is another set of concepts called with and without replacement. We're also going to talk about what's called a trial and what's called an experiment. So first, with or without replacement refers to how we structure our events or trials when we may or may not change our sample space. So first, what is a trial? When we have consecutive events, then we call each event a trial. For example, when we flip a coin twice, each flip of the coin is called a trial. So the entire experiment, which is actually just a set of trials, is made up of two trials, right? Flip 1 and flip 2. Our sample space is going to be then all the combinations of those two trials. And we've seen this before, like heads and heads, heads and tails, tails and heads, and heads and heads. Okay? Now, when I'm conducting an experiment in which I have multiple trials, the question is whether or not I can actually, when I select one of the values, does it get put back into the set or does it get taken out of the set? Okay? So with replacement means that after each trial, we will replace the elements that we took out for that trial. And without replacement means that once an element from the sample space has been counted, it is no longer available for further trials. Okay? So the wording may be a little bit complicated, but let's get an example so that you can kind of see what we might be doing here. Okay? So let's suppose that we have a flower shop. Okay, so we have a flower shop. And in the flower shop, we have 7 tulips, we have 8 roses, and we have 3 daisies. Okay? And what we want to do is we're going to say, you know what? Let's say a person comes in and they want to buy some flowers, right? And so we say, well, I want to know what's the probability that, say, for example, they pull a tulip. So the probability of a tulip, okay, that's going to equal 7 out of 18. Because there are 7 tulips and 18 total flowers. So 7 out of 18, that ends up equaling 0.389. Okay? Now, what about if I ask the question, well, now they want to pick a rose. So what's the probability that they pick a rose given that they just picked a tulip? Well, it actually kind of depends. It depends upon whether or not we're going to put the tulip back in. So we need to know, are we with or without replacement? Let's say, for example, we are with replacement. So when we do with replacement, we go from 7 tulips to 6 tulips, okay, and then we go back to 7 tulips because we're going to replace the tulips back in. So the probability of getting a rose is now 8, okay, out of 18 because we have 18 total flowers still. We replaced the tulip back in, so there's 18 of them. What about if we did it without replacement? Given that we just pulled a tulip, okay, and we'll do this without replacement. And so if we look at that, we have 8 roses still, because I didn't pull a rose the first time around, but our total went down. This 7 became a 6. Okay, so it's now 8 out of 17. Which is 0.471. 8 out of 18, though, is 0.444. So how we choose it, whether or not we're going to choose with replacement or without replacement, actually changes the probability. Okay, let's do another example using these same ones, and this time let's look at a probability of picking a tulip, given that we picked a tulip the first time around. Okay, and we'll do that again with replacement. So now I picked a tulip, and I'm going to put the tulip back in. So actually, I don't have 6, I have now 7. I took a tulip out, but I put it back in. So now I have 7 tulips out of 18 total tulips because I still have 18 tulips. Well, what if I do it without replacement? Now, if I do it without replacement, I've taken a tulip out, so now I only have 6 tulips left. And my total's also going down by 1. So 6 plus 8 is 14 plus 3, that's 17. So now we have 17 total flowers. Okay? In the first case, 7 out of 18 is 0.389. And 6 out of 17 is 0.353. So the probability is changed when we do it without replacement versus doing it with replacement. Okay? So that's how we think about with and without replacement. It's actually a way of thinking about how we're going to structure the sample space when we do something called multiple trials, when we're doing one event after the other. Okay? Now, I want to show something because with and without replacement has an impact upon independence. Okay? So its effect on independence. Remember that if the probability of B does not equal the probability of B given A, okay, then the two events are dependent. Or dependent. And also, if the probability of B equals the probability of B given A, then we have independence. So what's the upshot for this with and without replacement? Let's consider those things where we are looking at something with replacement. And again, we have our flower shop. Okay, so we've got 7 tulips, 8 roses, and 3, what do we have? Are they lilies? 3 daisies. Okay. 3 daisies. The probability that the second as a tulip, independent of everything else, or actually that an individual flower is a tulip, is going to be 7 out of 18. Without any condition that that's going to be 7 out of 18. We're going to just assume that that's going to be the case. And the probability that the second is a tulip, given the first is a tulip, when we're doing it with replacement, equals 7 out of 18. Because what we've done is we take a tulip out for the first one, but then we put it back in. So what we've done is we haven't changed our sample space any, and our probability remains the same. So consequently, notice that in this case, these two probabilities, they're the same. 7/18 equals 7/18. And what does that mean? It means that with replacement, picking flowers is independent. 2 flowers are independent. And that makes sense if you think about it from the perspective of if I go in and I conduct an experiment, right, and the first trial I do something and then I just replace it exactly back in, then the probabilities haven't changed because each trial is the same from one to the next. All right. So consequently, what we get is that anytime we do anything with replacement, where we're gonna like replace everything back into the sample space, we end up with independence. Okay. We end up with something that's independent. Now, what I should state is that we have a lot of trials or experiments in which this happens automatically. For example, flipping of coins. Okay. So let's say, for example, our experiment is flipping 2 heads or flipping 2 coins. flipping a coin twice, rather, is what I should say. The probability that the second is heads equals 1/2, or 0.5, and the probability that the second is heads, given that the first is heads, is also equal to 0.5. Okay? So consequently, what does that tell me? That actually tells me that these two end up having the same probability. And it makes sense, because you flip the coin once, right? You have a probability of heads. The second time around, the coin actually remains the same. It doesn't change as long as it's fair. And so consequently, what we say is that it's actually the same as doing something with replacement, because it's the same from one trial to the next, to the next, to the next. All right? So the upshot of this is that if we do anything with replacement, any kind of set of trials with replacement, we automatically get independent events. And there we go.